How much was lost?
It hasn't been like this as a one time kind of.
Oh, I'm gonna hit it.
Have you been keeping the actual video files on hand? Like you're not deleting them as soon as you upload them?
I put them on YouTube. I then send the link or post the link somewhere. But all the original files I should still have.
Because it might be you just out of space. That happens a lot on like Androids. It'll tell you
No.
how much space you have left for recording.
Yeah, the times that's been an issue is that it pops up with a warning.
Oh, like it just did right now?
No, that's a different warning. I don't know what the deal is with that one. It's also not part of any plan.
Oh, okay.
And when you first boot it up, it says, you have a message.
What?
Yeah. All right, well, let's see how long this one goes.
Alright.
All right, so the rules of thumb are those, we're good?
Yeah, thank you.
All right, now that Jake's gone.
We shall continue class.
You need me to go to the other Jake? No. I think of you as Jacob.
Fair enough. That's what I prefer.
Okay. All right, so we got a paper, so we have the initial setup here. They're 10 by 10 meters, or 10 meters by 10 meters. There's a 5 centimeter gap between them, 0.05 meters. And they're hooked up to a 15 volt battery. And, all right, so the first thing we do is stick a dielectric in between. If we put a dielectric in between, what is that result going to happen? What's going to happen here?
You increase the capacitance.
Yes, you will. By how much?
I know this 3.5.
Yep. The fact that his paper is irrelevant. The crucial part is the dielectric constant.
If we ever don't insert a dielectric, we just assume the dielectric constant is 1, right?
Yes, absolutely.
Which is why there's like a slight variation in the formulas, depending.
Right, whether you drop to sub-zero or not.
Oh, okay.
You have a question?
Could you just go over that like last step? Oh, sorry.
Okay. All right, we start out with just a capacitor hooked up to some power supply. We stick a dielectric in between it with a dielectric constant of 3.5. One of the purposes of a dielectric is to increase the capacitance or increase the charge that's on the plates, if we can. It's still connected to a battery, so yes, we can build up the charge on the plates. Dielectric also has a secondary function, is the fact that with a dielectric there, we can get the plates closer together physically, which would also increase the capacitance. So we start out with, initially, what's the voltage across the capacitor?
15.
Yeah, it's set. What about after we stick the dielectric in there?
15.
Yeah. And let's worry about I said voltage from the negative plate to positive plate, so it's positive 15. Which of these is the positive plate?
The one on the left.
Because it's next to the positive side over here.
Oh,
That's a negative plate. So then we're going to disconnect the battery. So I just got. If I disconnect the battery, how does that affect the voltage?
Should it drop to 0?
No, there's still charge on this. There's still a potential difference.
I mean, it changes though, but using equations, I don't know based on the relationship of the dielectric, but I do know that it changes.
Oh. Does it turn negative for some reason? Cause it's changing
No.
from,
No, this is still a positive plate, and that's still a negative plate.
but now we just gotta disconnect the battery.
Yes, from going from here to here, we disconnect the battery.
Shouldn't the voltage stay the same?
Why?
Because the distance between is the same? Oh, no, I forget the one.
Ultimately, there are a couple
Yeah.
pieces to that. Just disconnecting the battery doesn't change anything. It's,
Mhm. But if you then like mess around with the capacitors, like change the distance or so forth, then it does change the voltage, right?
absolutely.
My problem was trying to apply logic.
I'm sorry, I missed that.
See, my problem was trying to apply logic,
Ah,
like no battery, no voltage.
Well, like the
yeah, well, as
charge-
long as this is charged, we got a voltage there.
Okay.
Well, cause like the charge moves onto there, but when you turn it off, the charge is just stuck there on the plates.
Yes.
Oh, so it can't move anywhere.
Yeah,
Right.
it's just stuck there.
Oh, okay.
So now whatever we do, voltage could change if we start messing with it, just as Raphael said. Charge won't at this point. Charge is now set. Whatever the charge was here, it's the same charge here, it's the same charge here.
Okay.
Voltage, on the other hand, yeah, voltage doesn't change at this point, but it might change over here. It probably does.
Yeah, probably.
And then the last one, I think we triple the space inside.
Yeah.
And magically keep it filled. So this is now 0.15 meters. Sure, we can stick those on there. So my voltage will change now.
Cause there's more distance?
Yes, because there's more distance. All right, so let's hit some of the others and then we'll talk about. Potentially, you know what the new voltage is, but let's get some mathematical evidence before we just, unless somebody wants to speculate.
Wait, so let's say we triple the distance, but we haven't disconnected, the voltage would just stay the same, and then even after the disconnect, it would still stay the same.
Yeah, if all you do is disconnect, everything stays the same.
Mm-hmm.
It just allows for change later,
Okay.
which I think you had expressed.
Mm-hmm.
But it's gonna change because we moved it farther apart.
Yeah, voltage will change now. All right, we'll come to it. All right, so we got that, what else? Capacitance. How do we find capacitance?
K epsilon sum naught area over distance.
Kappa.
Sorry.
So in the first setup, 0. Oh, sorry, kappa is 1. So I get 8.85 times 10 to the negative 12 in SI units times an area of 100 in SI units over 0.05. What's the capacitance? Thank you. Sorry, didn't do my customary, if someone would be so kind as to calculate that.
One 1.77 times 10 to the negative 8th farads.
1.77 times 10 to the negative 8 farads.
Yeah, that's what I got as well.
Okay. When we stick the dielectric in there, what's gonna happen?
Well, you change, it's gonna be multiplied by 3.5.
Yeah, I mean, straight up from the formula, kappa,
Oh.
kappa goes from 1 to 3.5.
Oh, so right now it's nothing. We got 1. K is
Yeah,
1.
kappa's 1.
Okay.
But at this point, we multiply times 3.5 and get something magical. I guess still times 10 to the negative 8 farads.
Oh, sorry, 6.195.
Jacob, you got the same? Now we disconnect the battery, what happens?
Does it die? Okay.
Yeah.
Nothing.
And now we expand that distance by the factor of 3.
So divide by 3, or do you multiply by
Well, if the distance is 3 times larger, you would,
5 by 3?
you'll end up dividing by 3.
0.065.
Oops. Got the farads there, that's that answer. Now, if you prefer to do 20.65 nanofarads, fine.
Would that be engineering notation?
What, do put it in nanofarads or this?
If you did 20.65 nanofarads?
It would be, or 20.65 times 10 to the negative 9th. Engineering notation tends to have the exponent as factors of 3.
Okay.
At least that's what the calculator does.
I was trying to see if I remember it that way.
All right, so we got capacitance, charge. How do you find charge?
Capacitance times voltage.
Because we have another formula for capacitance. The capacitance is equal to charge divided by the voltage, maximum charge over the voltage. And so the charge, maximum charge, is C delta V. So we just multiply that times 15 to get the charge here. And then multiply those to get the charge here. Those to get the charge here. Well, it should be the same as here.
So the first scenario, it's 2.655 times 10 to the negative 7 coulombs.
And then the next one.
I got 9.2925 times 10 to the negative 7th coulombs.
That seems reasonable. Did you multiply those together or just multiply this times 3.5?
I multiplied the voltage times the capacitance we found.
Okay. And I do want to point out, it's been pointed out before, this C right here is coulombs, this C right here is capacitance.
I mean, that's fair.
Uppercase,
You don't wanna-
lowercase, we got 100 letters using Greek and our alphabet. We're gonna, at some point, we have to repeat.
Why don't you just combine letters?
Well, they did sort of, at one point by taking, it's called H bar.
See, I don't know what Bozo thought that 6 mu's, like they couldn't choose theta, like something.
You don't like. That's the letter, right?
The mu. The mu is the one that looks like a U with a stem up front.
Oh yeah, oh yeah.
We use that for like 4 different formulas.
They
Right.
can't use like
It's
AA
like-
or something?
Oh, start using double letters? They probably could have, but they decided not to.
I
Or
think
just
it's like-
make up a symbol.
Yeah,
I'm saying,
and that's it, again, H
Yeah.
bar.
You shouldn't submit our
Which is
complaints.
H divided by 2 pi, by the way.
That's what that is. H bar.
H bar is H divided by 2 pi, H being Planck's constant.
Oh, that's why the lines are there because it's just H divided by something.
Yeah, sure, let's go with, that's why they put the slash through it.
That's what we're going for.
It's probably, I've run out of letters. How about if I just make a change here? What is-
let's just start using runes at this point.
Runes?
Yeah. Just start using runes.
Just everything's a hieroglyphic.
Why not? Hey, they use mu.
They have to, to some extent. All right, so we have the charge here. So the charge at this point, when we disconnect,
The same
Same.
thing as in scenario 2.
so 9.2925 times 10 to the negative 7 coulombs. And then when I expand it,
Well, now you have to find the new voltage.
Then we don't,
Charge stays the same.
yeah, because we disconnected.
Ah. Nice. So we still would have to find the voltage though, right?
Yeah, we still need to, but now that we have the charge here, we can, using the formula over there. There was one test where I said, just assume that this value right here is C sub 0, and this would be Q sub 0, just sub 0 for all the initial values. That way you're not having to play around with a calculator. So this would just be 3.5 times C0 and 3.5 C0 and 3.5 times 3 C0. No, 3.5 over 3 C0. But I found most students still calculated the whole thing out. Did not save any time.
Also, do you want the voltage?
Yeah, what's the voltage?
45?
Yeah, it's just 3 times.
Yep. At least I knew the ballpark it should be in. If just expanding it out like that does not change does not change voltage by an order of magnitude. So if I had come out with times 10 to the negative third or something like that, I knew something would have gone wrong.
The board is trying to shut down.
Thank you. How impatient. All right, so we've got, what's left? Then the electric field. Now, in the wording of the question, I said, what's the electric field strength between the plates, from the plates, and the total electric field strength between the plates. But down here, that's really not the symbol for electric field strength. Properly, I either should put absolute value symbol, the absolute value around it, or drop the vector symbol. But since dropping the vector symbol might make it look like energy, I should put the absolute value symbols around it. But anyway, how do we find electric field?
The voltage over the distance.
All right, so we have delta V is equal to, technically, delta V is equal to negative E dot delta S. If the electric field is constant in space, as opposed to time.
That's what I was thinking of.
If the electric field is constant between the two plates, no matter where you are between the two plates. All right, so we are assuming, actually, why can we assume the infinite plate approximation? Why can we assume the electric field is constant?
Because it's a 10-meter plate and it's only a couple centimeters between them, so you said it was like a specific percentage. You said if it's small enough of a distance in between them compared to the size of the plates, you can assume it.
Absolutely. 10% is generally a good mark. So so we could make the approximation up to basically 1 meter between them. Using that rule of thumb. All right, so therefore, since I care about the electric field strength, I'm not worried about the sign there. Electric field strength, again, is just the magnitude. Is this going to find us the electric field between the plates, from the plates, or the total?
Total.
Yeah, and this is total. So, in the first case, it's 15 volts divided by 0.05 meters. Doing the fancy math there, 300
Yep.
units.
Newtons over Coulomb?
4?
Farads?
No.
That's different, okay.
I don't know. I guess you could do anything if you really want to.
Well,
Voltage
Volts
over
over
meter.
meters?
Yeah, just because some students will input newtons per coulomb, which is where my mind goes, but some people do volts per meter, and then I have to go, oh, wait a second, is that newtons? Oh,
So either way, you're good?
Pardon?
Either way, you're okay?
Yeah, they're both equally correct. You don't have to do both, please don't do both. Pick one or the other.
But if I do like both and then like divide by 2.
Say that again.
If I do both the units and then I divide the units by 2.
Oh, do both.
Divided by 2.
Yeah,
There you go.
that,
Is that technically
Is that
correct?
what it is?
that would violate the 1 fraction bar per unit.
Aw. Can we?
So I probably would laugh and then take a point off.
Should never.
Hey, this is America. We don't follow rules.
I do recognize if you multiply them, then you have to do a square root.
Back.
All right. So a volt per meter is equal to a Newton per, see, a coulomb is an ampere second. Therefore, a second would be a Newton meter per volt ampere.
Oh, that kinda makes sense.
Another unit of time.
I feel like you've shown that to us before.
I've done that one.
Thanks.
Yeah, you did that one.
There's a slew of them, so
Or it
I,
was another second.
oh, I know I've done at least some other kind, but if I've already done this one, I apologize. I will try to give you different units of time.
You should make a video on just like.
All the units of time?
Yes.
So no
I should.
more Virginia?
I will watch.
30 minutes later. He's like, and that's all the stuff from physics 251. Now we'll move on to 252.
All right, so, and so it's just a matter of going through the same process for the B over there. Or I guess, we set it up, A, oh, this is A initially. That does not work.